My name is Efekan Kokcu. Thanks for the nice introduction, Ermal. I'm here to present you the algebraic methods for quantum simulation of many-body systems. So first of all, most of the work that I'm a new postdoc, most of the work that I'm going to present today are done during my PhD. So I need to say hi to all NCSU folks that I work with. Alexander Kemper is my my PhD advisor, and Kemper Lab collaborates with all of these people, including my current advisor Berkeley and a lot of other LBL folks. So most of these works are done in collaboration with all of these people. So the outline of this presentation, I was a bit ambitious, and I thought that I would be talking about all of these things. That's why the abstract is a little bit kind of long, but I might need to skip some of these. So first, I'll be talking about quantum simulation by quantum computers that I have a feeling that most of you actually already know. So I'll actually speed up that part. Then I'll need to talk about dynamical Lie algebras. How many of you are familiar with Lie algebras and dynamical Lie algebras so that I'll have a feeling? Cool, I gotta talk about that. Great. And after that, I need to talk about how to use dynamical Lie algebras. There are two different ways. Either look at it globally or locally. And in those, I will be talking about 3 different papers, basically. And all right, good luck to me. I'll talk about quantum simulation by quantum computers first. So, well, this is the slide that you show to people that you're asking for funding. That you're basically talking about many-body systems are hard to simulate. The reason is Hilbert space dimension is extremely large, and simulating something like I don't know, a long protein by using the best supercomputer takes years and stuff like that. So we need quantum computers to simulate these things like electronic structure problems and etc. So basically, we need quantum computers because Hilbert space dimension scales exponentially for these systems that we want to simulate. I'm going to mainly speak about time evolution rather than, for example, finding ground state of these systems. Quantum simulation can be just separated in a couple of different pieces. So because I'm going to mainly talk about time evolution, I'm mostly going to talk about Schroeder-Suzuki decomposition in the beginning to give you a feeling of what you did in the NISQ era to time evolve these many-body systems. So for that, let us consider a 5-side pair chain. So these are not Roman numbers. This is not 23. That is this is an XX interaction between spin 1 and spin 2, and then these are identities. This is some notation that is easy for us to do. And then this one is a YY interaction between qubits 2 and 3, and then you know the drill. A, B, C, D are basically some real numbers. I just kept them arbitrary to show how generic this method is. So time evolution is done by exponentiating this Hamiltonian. You multiply it with minus IT. T is your simulation time, and then you try to exponentiate. And luckily and unluckily, this exponentiation cannot be done in this way. I mean, this being not being able, us being not able to do this way is the reason that we are all getting paid. And the reason is that this XXIII and IYYII, those terms basically do not commute. If they commuted, life would be easy, but they don't commute. However, when the simulation time is small enough, you can approximately do it. So it's when the simulation time is replaced by something that's called epsilon, that is the universal symbol for small enough real number. You basically can write this way plus some quadratic order error. And that allows you to write a bigger time evolution by using these small time evolution steps. So if you want to write some u of t, let's say that t is 1,000 epsilon, then you can basically write this u of epsilon, you append 1,000 of them, and then you have your u of t to order O of 1/1,000 error. So that's basically how you apply Schroeder-Suzuki decomposition to build a quantum time evolution circuit for a many-body system like this. So there are a couple of problems with this. Number one is currently quantum computers are noisy. So these beautiful Lego-like pieces that you see here are not actually just like perfectly Lego-like pieces. They have tiny bits of cracks. So the bigger tower that you build from these Legos, less stable it will be. And if you want to do long time simulations or the time evolution with less error, you would need a lot of trotter steps, and your hardware will start to give you garbage after some point. And if you try to reduce the number of steps by simply increasing the epsilon, then you will have theoretical error in trotter. And there is basically some like tug of war between the theoretical error and the hardware error that you want to choose. So we wanted to address that problem by reducing this trotter circuit that you obtain. So like the remaining part of this will be entirely focused on how to compress this further. Okay. So for that, there is something that is called dynamical Lie algebra that I need to define. Again, let's consider 5-side Kitaev chain. So, but this time I just want to rename these like the Pauli strings that you see here as HI so that I can just like use it for convenient notation. So when you try to compress these circuit elements, circuit gates, like Pauli string exponentials, eventually what you're going to be trying to do is you need some product of e to the power of some coefficients times some Pauli string. And then these Pauli strings will be n-qubit Pauli strings. And the fancy way of saying that these are in SU2 to the power of n. And when you're trying to compress them, eventually what you want to do is like you have some e to the a, let's say that this is like this xx, and then you have this e to the b, let's say this is this yy, and you want to sort of combine them, like mash them together. And what you actually end up having is it is e to the power of some mess. All right, so it's not just a plus b as I told you, but like it will contain things like a comma b, a comma b, and etc. I think all the physicists already know this notation. But in case no one, like there are people who don't know, a comma b is a times b minus b times a. It's the commutator. I forgot to put that equation, I'm sorry. But what happens is you need all nested commutations of this a and b like to express this exponent that you see here exact manner, okay? So that's why we build this set that is called dynamical Lie algebra. So I'm just going to go back and forth a little bit. So here, as you can see, there's A, there's B, and then you have all the nested commutators. And in the circuit, we have terms of my Hamiltonian, XX, YY, XX, YY, right? So here, I just generate the nested commutators of all the terms in my Hamiltonian, and I put them in a set. Eventually, this is going to be a finite set for n-qubit calculations, because I know that it should be definitely less than 4 to the power of n, which is the dimension of this dynamical algebra that you see here, and this Lie algebra that you see here, and most probably, and in most cases, that actually like, turn out to be way smaller than this set of operators that we have, which is called SU2 to the power of n. So that is why the dynamical algebra is basically defined. So that allows us to replace this SU2 to the power of n by the DLA that we defined here. And at the end, it will be reducing the number of gates that we need to use and possibly reduce the circuit depth from like arbitrarily large to some fixed number, okay? So here's a toy example to give you a little bit more of a feeling. Let's consider 3-side Kitaev chain instead of 5. So in this case, we have only 2 terms in our Hamiltonian, and then a traditional trotter circuit will be like this, an indefinite length. However, the dynamical Lie algebra turns out to be just 3-dimensional in this case. That's why it's a toy example. And then what happens is you can basically write any time evolution with any simulation time for this model by just using like a YY XX YY gate or XX YY XX gate. Like you can basically prove all of these things because this is SU2 and this is basically Euler-Anger decomposition. All right, so this is sort of like the idea behind DLA. Like we're just trying to figure out like if the DLA is small, maybe we'll be able to compress it down. All right. So there's a global way of looking at this. which is, I'm just going to go back and forth again. I'm sorry. We need to write this U of t as a product of these, and then I need to find like these kappa I angles. I need to find out what these sigma I bars are. And I found those sigma I bars are in terms of DLA, but like, how am I going to find these kappa I's? So this is the global way of looking at it. I had this entire system. I look at its DLA, and then I need to find these angles. And to do that, we did a project using Cartan decompositions. And I will not be able to talk about all of these things, but steps are you build the DLA, and after you build the DLA, you separate the terms into two pieces. And then after that, there's some, like quantum is dark magic, but this is even darker magic that I don't know exactly. I can prove it, but I don't have any intuition. You can sort of diagonalize your Hamiltonian by using only one set of these generators that you generate. Like this split is Cartan decomposition, and you use like the K part of that Cartan decomposition to sort of diagonalize your Hamiltonian. And after that, you obtain a fixed step circuit, as in it is independent of the simulation time, because time only enters as a parameter and your circuit structure remains the same.
Little h,
yeah. The little h ends up commuting. That's why I say like a sort of diagonalize. Like when you diagonalize something, it consists of diagonal matrices. So all these little h's will turn out to be all diagonal matrices. They will commute with each other. Sort of diagonalizing means these h's are not diagonal, but they commute with each other. Yeah, good question, good comment. But like the one thing that we found out is like you can basically also like shuffle all of these things, all of these red ones all together, and then like find the angles after that, no problem. The darker magic part that I talked about is like the method. This is like a horrifying slide. You don't need to read all of it, but like there's a cost function. You need to minimize it, but you don't need to find the global minimum of it. Only local minimum works. So mathematically, it's easy to prove. I still don't have an intuition for it. I'm sorry. But if you want to look for the proof, you can check the paper, or you can talk to me after that. I will be happy to talk to you about. So by using this method, on the original paper that we introduced this method, we did Anderson localization on TFXY, where there's like a not localized phase, and then there's a localized phase. You compared it to Trotter. Of course, our method did better because it always generated fixed step circuit and like with no theoretical error except the optimization error that can be arbitrarily small. However, Trotter gives you more error, and then it eventually, for longer simulation times, it gives you worse results. And then one of the co-authors in the paper applied it to run a dynamical mean field theory on a four-side Anderson impurity model on actual IBM quantum computers. He was interning in Oak Ridge, so he had a lot of access. I think he ran like 15,000 circuits within 2 months or something. And he was able to see the Mott insulator transition by using our method. And one of the sole reasons is that it always gives you a fixed step circuit, like the structure always remains the same. And because of that, your hardware noise always ends up being the same. And if you're only looking for frequencies, that's basically great because you do Fourier transformation and you detect frequencies easily. Amplitudes go down. Amplitudes are basically shuffled. They're really bad, but the frequency peaks are really visible, okay? So I really suggest you to check those papers. And after that, we saw that like dynamical Lie algebras and Lie algebraic methods were really good for simulating many-body systems. Then we basically paired up with one of the mathematicians in North Carolina State University, Boško Bakalo, and then decided, why don't we classify all of them? So this here, I'm just going to conceptually talk about it and don't give you details. I'm just going to flash you some slides just to scare you. But the thing is, like, when you talk about a bunch of spins or a bunch of qubits, what we're dealing with is we want to do only 1 or 2 local Hamiltonians. Basically, you have magnetic field and then spin-spin interactions. It can be on any lattice. Basically, here I give you like the linear lattices. It doesn't have to be linear. But we have answer for, so basically, we classified all the generators first. These are the generators that we end up having all sorts of interactions that we need to put on every edge and every qubit. And then we classified all the Lie algebras. only takeaway that you need to take from here is like we saw different dimensional scalings for these Lie algebras. A good portion of them scales exponentially. Some of them scales quadratically. Those are the free fermionizable ones. And then some of them scales linearly. Those are the complete abelian ones. So this is the takeaway result from this. But like, if you wanna, for example, figure out if your variational ansatz is expressive enough, all you need to do is like go to one of these papers and then check like which dynamical Lie algebra that your ansatz fall into, and then you'll be able to see if it is expressive or not. So this is a classification paper in that sense. Now, finally, I only have 30 seconds, so I'm just going to skip through this. Going back on this slide,
question. So when you say that you classified all of them, you proved that there are no other dynamical Lie algebras that can exist.
So yeah, within the choices that I made. So like we basically have chosen such a way that like these edges are always going to be like if you have XX interaction between these two, there is another XX interaction between these two as well. So we in our cases we don't alternate those things. And also the other thing is like we only consider Pauli strings. So like for example, we don't have anything like these are the translation invariant ones, or like these are particle conserving ones. Like we basically consider only the Pauli strings, and then for an arbitrary coefficient, like every coefficient completely different, then we get the dynamical Lie algebras.
The interaction is two qubit interaction.
Yeah. 2-qubit interaction and 1-qubit interaction.
And does it have to be symmetric with on the 2 qubits, or can it be? So if I have a term in my Hamiltonian that's like xy, do I also have to have yx?
So for the second paper here, yes. For the first one, no. For the first one, we did it only for linear and all-to-all connected and ring topologies. But when you try to do it for every graph, we did it only for undirected graphs, which means that, yeah, like when you have xy, you're going to have yx as well. Those are great questions. Also, there is one more work that I actually forgot to cite. I'm so sorry that it's not our work, it's someone else's work. John Iser's work, that they actually like have answer for even alternating versions as well, that kind of like covers our case here, which actually like came out around the same time. So you can check that out as well. In the interest of time, should I stop or? Okay, one more minute, thank you. All right, so when you look at the dynamical like Lie algebras from this point of view, like I assume that like most of you attended Biscuit meetings, you can look at your like Biscuit meeting yesterday. You can look at this system instead of by looking at the entire qubits. You can just like look at like 2 or 3 qubit versions, like the parts of this Trotter circuit. And then if you have structures like this that we observed in Kitaev chain, then you basically can use that to compress. And this is how you do it. If you have gates satisfying these kind of properties, then you basically can shuffle them around and use it for compression. So for example, here you have this structure, and then one more gate is coming from right. You can basically, using these three things, you can basically push it down and merge this thing to 5, and then end up having only a triangle only, which means that like no matter how many of these gates you have, you can always truncate it into a triangle, and then even turn it into a more efficient depth circuit. We found a bunch of examples for this, but like the most general thing that we found was like free fermions hopping from like whichever lattice point to lattice point, basically free fermions on any lattice. We simulated 4x4 tight binding, got these results, and thank you.
One question. You have this classification of algebras, right? For the ones that aren't exactly solvable or free fermionizable, is it still possible to compress circuit for the exponentially scaling one?
For the exponentially scalable ones, like, so it's not possible to do it exactly, maybe variationally. There are different methods, like there are a lot of papers that actually try to do it in a variational manner. It is also kind of like state dependent, but currently, like all of these methods that we did are exact. So it's like, I mean, that you can do it in arbitrary precision. And because of that, it is kind of limited to integrable models, unfortunately. But like we have been looking for certain approximations, like maybe perturbative approximations and stuff, for the Cartan decomposition one. And like for this compression-wise kind of a thing, there are a couple of different methods using, like, this is not our group, like a couple of different methods using, like, for example, matrix product operators to compress different layers of circuits. And there are a lot of compilers out there like Biscuit and like that actually like does these things. Yeah, of course.
Thank you.
Sure.